For the last 4 years, every AI image you've seen was generated by a diffusion model. But the biggest AI labs in the world just quietly killed diffusion, replacing it with a far more elegant mathematical concept: flow matching. Here is exactly how it works. Diffusion models earned that 4-year reign honestly. DALL-E 2, Midjourney, Stable Diffusion, Imagen. Nearly every headline image generator you've used was, underneath, doing the same strange thing. It started with pure noise, a canvas of random static, and slowly, step by step, denoised its way toward a coherent picture. It worked so well that diffusion and generative AI became almost synonymous. But that success was hiding a very expensive mathematical habit. Underneath every diffusion model sits a stochastic differential equation, an SDE. Stochastic is just a precise word for random, and that randomness is baked into the math at every single step. To turn noise into an image, you don't take one clean leap. You take hundreds of small, jittery steps, each one nudged by fresh randomness, each one only reliable if the step before it was small enough not to break the approximation. That's why early diffusion models needed 1,000 steps to generate one image, and why even optimized versions still need dozens. Simulating a random walk is computationally exhausting, and exhausting is expensive at the scale of 1 billion users. So the frontier labs went looking for a replacement, something that keeps the part of diffusion that worked, learning to transform noise into data, while throwing out the part that didn't: the randomness, the tiny steps, the sheer computational drag. What they landed on is called flow matching, and it now sits underneath systems like Stable Diffusion 3 and Sora. To actually understand it, we're going to build it from the ground up, starting with a 200-year-old problem about moving piles of sand. Diffusion's mathematical engine actually has a name worth knowing before we move on: score-based generative modeling. Instead of learning the image directly, the network learns the score, the gradient of the log probability density, essentially which direction makes a noisy sample more likely to be real. Follow that gradient, add carefully calibrated noise back in at every step, and you slowly climb out of static into a coherent picture. It's a genuinely beautiful piece of stochastic calculus. It is also, as we're about to see, mathematically overkill for a problem that turns out to have a far more direct solution. In 1781, decades before anyone dreamed of neural networks, a French mathematician named Gaspard Monge asked a very physical question. Imagine a pile of sand, call it a remblai, that needs to be moved and reshaped into a hole somewhere else, a déblai. There are countless ways to shovel that sand from source to destination. Monge wanted to know, which way moves it for the least total effort? 2 centuries later, this exact question turns out to be the mathematical skeleton underneath modern generative AI. Picture it visually. On the left, a chaotic mound of sand, that's your noise distribution, a shapeless cloud of random points. On the right, a hole shaped like something specific, a face, a cat, a landscape. That's your data distribution, the actual images you want to generate. Generating an image, in this framing, is nothing more than deciding how to move every single grain from the noisy pile into the shape of the whole. Every grain needs a path. The only question is which set of paths costs the least. Cost here has a precise meaning. For each grain of sand, multiply how far it travels by how much of it you're moving, and add that up across every grain. Move a grain of sand a huge distance, and you pay a huge cost. Move a whole pile a tiny distance, and you barely pay anything. The mapping that matches every source point to a destination point while minimizing this total cost is called the optimal transport map. And Monge's insight was that, no matter how many valid ways there are to shovel the sand, exactly one of them is cheapest. Monge's original version had a stubborn flaw. It demanded that each grain of sand go to exactly one destination, a rigid one-to-one matching that doesn't always exist, especially when the pile and the hole aren't the same shape. In 1942, the Soviet mathematician Leonid Kantorovich relaxed the rule. Instead of insisting each grain go to one place, he allowed mass to split, a fraction of a grain here, a fraction there, governed by a transport plan that's really a joint probability distribution over sources and destinations. This relaxation is what turned Monge's stubborn geometry problem into the smooth, solvable optimization that modern machine learning actually uses. Together, this is the Monge-Kantorovich problem. Now swap the physical metaphor for the statistical one, because that's the form generative AI actually cares about. The pile of sand is a probability distribution. Call it P0, simple noise, usually a Gaussian. The hole is another probability distribution. P1, the distribution of real images, impossibly complex and high-dimensional, but still, mathematically, just a distribution. Optimal transport asks for the cheapest way to reshape one distribution into the other. And cheapest, measured this way, gives you something called the Wasserstein distance, a way of measuring how far apart two distributions are, not by comparing their shapes point by point, but by asking how much work it would take to morph one into the other. Here's the payoff. If generating an image is really just transporting the noise distribution onto the data distribution, then training a generative model is really just learning an efficient transport map, a function that takes a noise sample and moves it to a data sample. Diffusion models solve a version of this implicitly, through thousands of small stochastic nudges. But if the optimal transport map exists as clean, deterministic geometry, the natural next question is obvious. Can we learn that geometry directly, without simulating a random walk to approximate it? That question is exactly where flow matching begins. There's a beautiful piece of rigidity hiding inside Monge's original problem that's worth knowing, because it foreshadows everything to come. When the cost of moving a grain of sand is the square of the distance it travels, the natural choice in continuous space. A result called Brennier's theorem guarantees that the optimal transport map isn't some wild, tangled function. It's always the gradient of a convex function, which means the transport paths it produces never cross each other. Points sort themselves into destinations in the most orderly way physically possible. That hint that the cheapest way to move probability mass tends to be strikingly uncomplicated is exactly the clue flow matching eventually runs with. An optimal transport map tells you where each point ends up, but it doesn't tell you how it gets there. To build something a neural network can actually learn and a computer can actually simulate, we need to describe the journey, not just the destination. That's what a vector field gives us, and it's the single most important piece of machinery in this entire video. Picture a two-dimensional grid covering the plane, and at every single point on that grid, draw a small arrow, a vector, pointing in some direction with some length. That's a vector field, a function that assigns a velocity to every point in space. Drop a particle anywhere on this grid, and the arrow at its location tells it exactly which way to move and how fast at that instant. Nudge it forward slightly, look up the new arrow at its new position, nudge it again. Repeat that infinitely often, in the limit of infinitesimally small steps, and the particle traces out a smooth, continuous path called a flow line. Mathematically, we write this velocity field as v of x and t, a function of both position x and time t, because the arrows themselves are allowed to change as time moves forward. At time 0, the arrows might all point one way. By time 1, an entirely different pattern. A particle's trajectory x of t is then defined by one deceptively short equation. The derivative of x with respect to t equals v of x of t, t. In plain language, the particle's velocity at every instant is whatever the field says it should be, right where the particle currently sits. This is an ordinary differential equation, an ODE, and unlike the SDE from Chapter 1, there is no randomness anywhere in it. Same starting point, same field, same path, every single time. Now the crucial generalization. Don't drop just one particle, drop an entire cloud of them, sampled from your noise distribution P0. Let every particle in that cloud follow the same vector field simultaneously. Because the field is deterministic, each particle traces its own smooth trajectory, and the whole cloud deforms continuously over time, stretching, rotating, compressing like a fluid flowing under a current. This is precisely why the technique is called flow matching. We are quite literally describing the flow of a fluid of probability. Here's the piece that makes this rigorous, rather than just a pretty animation. As the particles move under V, the probability density they represent evolves according to a well-known equation from physics called the continuity equation. The rate of change of the density equals minus the divergence of density times velocity. This equation is the exact same mathematics that governs how smoke disperses through a room or how heat diffuses through a metal plate. It guarantees something essential. If you start with the correct density P0 and follow a velocity field that satisfies this equation, you're mathematically guaranteed to end up with the correct target density P1. No randomness, no approximation, a hard mathematical guarantee. There's one more piece of vocabulary worth locking in, because you'll see it in every flow matching paper: the push forward. If a point x0 is sampled from P0, and phi t denotes wherever the flow has carried x0 by time t, then the distribution of phi t of x0 across all the particles in the cloud is called the push forward of P0 under phi t, written phi t star P0. At t equals 0, that's just P0 unchanged. At t equals 1, if the field was constructed correctly, that push forward exactly equals P1 real image data. The entire flow is one continuous, deterministic bridge between a distribution you can trivially sample and a distribution you actually want. So step back and notice what we've built. A vector field turns the static optimal transport map from Chapter 2 into a dynamic, simulatable process. Start anywhere in the noise cloud, integrate the field forward in time, and arrive at a sample from the data distribution. It's continuous, it's deterministic, and this is the part that will matter enormously in a few minutes. It's described entirely by ordinary differential equations, not stochastic ones. The only problem left is the one every machine learning paper eventually has to solve. We don't actually know what this vector field is. Real image data lives in a space with millions of dimensions, and nobody can write down its true transport field by hand. We're going to have to teach a neural network to guess it. Here's a subtlety worth flagging before we move to training, because it's the hinge the entire next chapter swings on. The vector field that correctly transports the whole cloud, the marginal field, isn't some separate object from the individual particle trajectories. At any point x and time t, it turns out to equal the average, weighted by probability, of all the individual conditional velocities of every possible trajectory that happens to be passing through that exact point x at that exact time. In other words, zoom in on a single location in the flow, average the velocities of everyone passing through it, and that average is, provably, the correct marginal field. That might sound like an abstract technicality, but it's the single most useful fact in this entire video. Computing an average over every possible trajectory sounds intractable. There are as many trajectories as there are noise image pairs in the universe. But averages have a well-known trick. You don't need to compute them exactly, you just need an unbiased estimator, something whose expected value matches the true average. And regression, plain, ordinary least squares regression, is exactly the tool that finds the function minimizing squared error to a noisy target, which converges to that target's true conditional expectation. That single fact is about to turn an intractable averaging problem into an ordinary training loop. Before we move on, hold a simple picture in mind, because everything after this stays true to it. Two dots on a plane, a noise point sitting up and to the left, a data point sitting down and to the right. The straight arrow connecting them is a velocity, constant, unchanging, the same length and direction the entire way across. Scale that up to 1,000 pairs of dots scattered across the plane, each with its own straight connecting arrow, and you get a field of parallelish lines sweeping the noise cloud toward the data cloud. Scale it up again to millions of dimensions, and the picture doesn't change in kind, only in size. So here is the actual machine learning problem. Train a neural network, call it v theta, with parameters theta, so that when you feed it a point x and a time t, it outputs a velocity that closely approximates the true, unknown vector field u that would correctly transport noise into data. Once that network is trained, generating a new image becomes almost absurdly simple. Sample random noise. Then integrate the network's predicted velocity field forward from t equals 0 to t equals 1, and whatever point you land on is your generated sample. The obvious way to train this network would be to first solve for the true optimal transport field u across the entire dataset, and then have the network regress onto it. But that's a dead end. Computing the actual Monge-Kantorovich optimal transport plan for millions of high-dimensional images is itself a brutally expensive optimization problem, arguably harder than the original task of training the generative model. If flow matching required solving optimal transport exactly first, it would have gone nowhere. The breakthrough insight, published in 2022 by researchers including Yaron Lippman, is that you don't need the true, globally optimal field at all. You only need any field that transports P0 to P1, and it turns out you can construct one explicitly, for free, by conditioning on individual data points. Take one real training image, x1. Take one random noise sample, x0. Now just define the simplest possible path connecting them, a straight line. This is the conditional probability path, and its formula could not be simpler. Write it out. xd equals 1 minus t times x0 plus t times x1. At t equals 0, this is exactly x0, pure noise. At t equals 1, it's exactly x1, the real image. In between, it's a linear interpolation, a straight line blend that slides smoothly from one to the other as t sweeps from 0 to 1. There's nothing mysterious in this line. It's the same linear interpolation you learned in a first calculus class, just applied to an entire image treated as one very high-dimensional point. Now differentiate that straight line with respect to t. Because it's linear, the derivative is beautifully constant, and it doesn't even depend on t. The target velocity is simply x1 minus x0. Think about what that means physically. It's the straight arrow pointing directly from the noise sample to the data sample, the exact direction and exact speed a particle would need to travel that line in unit time. We've just written down, in closed form, with no optimization required, a velocity field that transports this one specific noise point to this one specific data point. Here's where it all comes together into something trainable. Sample a random data point x1 from your dataset, a random noise point x0 from a Gaussian, and a random time t between 0 and 1. Compute xd along their straight line, and compute the target velocity x1 minus x0. Then train the network by minimizing the squared distance between its prediction, v theta of xd and t, and that target velocity. That's the entire flow matching loss, a simple regression objective, structurally no more complicated than fitting a line. And remarkably, a landmark theoretical result guarantees that if you minimize this simple conditional objective across the whole data distribution, the network converges to a field that correctly transports the full noise distribution to the full data distribution, even though no single training step ever touched that global problem directly. Sit with how strange this actually is for a moment. We wanted to learn a vector field that correctly transports an entire high-dimensional cloud of noise onto an entire high-dimensional cloud of real images. A global, population-level statement about two distributions. And the recipe that provably achieves it is, look at one noise point, look at one image, draw a straight line between them, and regress. No pair of samples ever needs to know about any other pair. The global transport problem falls out for free from millions of independent, local, straight-line examples. That's the quiet mathematical trick underneath the entire paradigm. This is precisely the argument, formalized by Lippman and collaborators, that makes conditional flow matching legitimate rather than a lucky heuristic. They proved that the gradient of the simple, per pair conditional loss from beat 4f, averaged over the whole dataset, equals the gradient of the true, intractable marginal loss we actually care about, the one measured against the real population-level vector field from Chapter 3. Optimizing the easy thing and optimizing the hard thing point in exactly the same direction. That's not a heuristic approximation. It's an exact equivalence, proven with nothing more exotic than the Tower property of conditional expectation. One more generalization worth knowing. The straight-line path we chose is the simplest valid choice, but it isn't the only one. The framework accommodates any smoothly varying conditional probability path between noise and data, including the curved Gaussian paths that classical diffusion models secretly use. That's a striking fact in its own right. Diffusion models are themselves a special case of this same conditional flow matching framework, just with a needlessly complicated choice of path. Flow matching, in its modern form, is really the realization that the straight-line choice was sitting there the entire time, simpler and just as valid. Rewind to Chapter 1 for a moment and look closely at what training a diffusion model actually demands. Its underlying stochastic differential equation has to be simulated, stepped through, moment by moment, with randomness re-injected at every stage, just to construct a single training example the network can learn from. That simulation is expensive, it's sequential by nature, and it compounds across every training example, every batch, every epoch. Now look back at what we just did in Chapter 4. At no point did we simulate anything. We picked a noise point, we picked a data point, we drew a straight line between them with one line of algebra. We computed its constant derivative with one subtraction. There was no stepping through time, no sequential process, no randomness injected mid-trajectory, just a closed-form formula evaluated once. This is what the flow matching literature calls simulation-free training, and it is the single biggest practical reason the field jumped so fast. Watch what happens to the geometry itself. Picture the chaotic, jittery path a diffusion model's SDE traces between a noise point and a data point. A squiggling, randomly perturbed walk that wanders before it arrives. Now watch flow matching's conditional paths in the same picture. Every single one is a straight line, edge to edge, noise to data, with no detour at all. The chaos doesn't get smoothed out gradually. It snaps, instantly, directly into perfectly straight, parallel paths connecting the noise cloud to the data manifold. That snap isn't just visually satisfying, it's the entire mathematical payoff. A straight line is the simplest possible trajectory a differential equation can describe. Constant velocity, constant direction, zero curvature. A neural network trying to learn a field made of straight conditional paths is regressing onto the easiest possible target. Batch by batch, with a training signal you can compute directly from data instead of sampling from a simulation. This idea has a close cousin worth naming. Rectified flow, developed independently around the same time, which pushes the straightness even further. After an initial round of training, you can repair each noise sample with the image it now tends to generate, retrain on those new straight line pairs, and repeat. Each round rectifies the paths further, reducing the curvature that remains from the network's own imperfections, until the learned trajectories are close enough to perfectly straight that you barely need to integrate at all. So state the payoff in one sentence. Diffusion trains on stochastic, simulated, curved paths that are expensive to construct even once. Flow matching trains on deterministic, closed-form, straight paths that cost one subtraction. Same underlying goal, transport noise into data, achieved through geometry that is fundamentally cheaper to learn and, as the next chapter shows, fundamentally cheaper to run. This is also, candidly, why this shift happened as fast as it did inside the frontier labs. Research teams don't retire a working technique because a new one is more elegant on a whiteboard. They retire it when the replacement is measurably cheaper to train, cheaper to sample from, and easier to scale, while matching or beating the same image quality. Flow matching hit all three at once. A simpler loss to implement, a simulation-free training loop that parallelizes trivially across a cluster, and a sampling process that got faster essentially as a side effect. That combination is rare, and it's exactly why systems like Stable Diffusion 3 and Sora rebuilt their generative core around it rather than patching diffusion once more. There's a pleasing twist to end this chapter on. In 2020, researchers Yang Song and colleagues showed that every diffusion model's noisy stochastic process has a deterministic twin, a probability flow ODE that produces the exact same marginal distributions at every point in time, with no randomness at all. That ODE existed the whole time, hiding underneath every diffusion model ever trained. Flow matching didn't invent the idea of a deterministic path from noise to data. It recognized that you could train directly for that deterministic path from the very first gradient step, instead of first learning a stochastic process and only extracting its deterministic shadow afterward. Once that realization landed, the field moved with startling speed. The core flow matching and rectified flow papers appeared within months of each other in 2022. By 2024, Stability AI's Stable Diffusion 3 had rebuilt its entire generative core around rectified flow. Within another year, simulation-free, straight-path training was the default assumption in new generative research, not the exception. 4 years is a long reign for any idea in a field that moves this fast, and the replacement didn't take another 4 years to arrive. It took about 2. That's the real shape of progress in this field right now. Not a slow accumulation of bigger models on the same equations, but the occasional discovery that an equation itself was never load-bearing in the first place. We've used both terms all video, so let's put them side by side precisely. An ordinary differential equation, an ODE, describes a trajectory with a single deterministic derivative, dx dt equals v of x t. Give it a starting point, and its entire future path is fixed. A stochastic differential equation, an SDE, adds a random noise term to that derivative at every instant. So the same starting point can wander down countless different paths depending on which random numbers land. That injected randomness is precisely why diffusion sampling needs so many steps. A numerical solver can only trust its approximation over a very short interval before the accumulated randomness invalidates it, so it has to reevaluate, re-inject noise, and recorrect constantly, dozens or hundreds of times per sample, each step a full pass through a large neural network. A deterministic ODE has no such constraint. Because the path is smooth and predictable, classical numerical solvers, the Euler method, or more accurate Runge-Kutta schemes, can take far larger steps while staying close to the true trajectory, since there's no random term to correct for between evaluations. Adaptive solvers can even stretch step size dynamically wherever the field is nearly straight, which, after flow matching training, is most of the time. This is where the abstract math becomes a very concrete product advantage. A diffusion sampler might need 50 or 100 network evaluations to render one clean image. A well-trained flow matching model, riding on straightened, near-linear paths, can often get a comparable result in 5 to 10 steps, and heavily distilled variants push toward a single step. That's not a minor optimization. It's roughly an order of magnitude fewer forward passes through a very large network, which translates directly into faster products and dramatically cheaper inference at scale. Picture 2, solvers racing across the same picture. The SDE solver creeps forward in tiny increments, constantly resampling a random kick, checking whether it's drifted too far, correcting, and creeping on a cautious, short-sighted walk. The ODE solver, riding a nearly straight field, strides forward in long, confident jumps, because the direction barely changes between one step and the next. It doesn't need to double-check against randomness that was never there in the first place. Same start, same finish, dramatically different number of steps to get there. So the 10x speed-up people cite when they talk about flow matching isn't a separate engineering trick bolted on afterward. It's a direct geometric consequence of everything in Chapter 5. Straighten the paths at training time, and you get to take giant, confident steps at sampling time. Translate the step, count directly into what it costs to run. A single forward pass through a large image or video diffusion network can burn a meaningful fraction of a second of GPU time, multiplied by every one of 100 sampling steps, multiplied by every image any user generates all day across a global product. Cut that to 5 or 10 steps and you're not shaving a corner. You're cutting compute, energy draw, and latency by roughly the same order of magnitude that made the improvement worth chasing in the first place. At the scale of hundreds of millions of daily generations, that difference shows up directly on a hardware budget and a power bill, which is precisely the kind of number that gets a paradigm adopted company-wide rather than left in a research paper. None of the mathematics in this video was specific to pictures. A vector field can transport a distribution over any kind of data, including video, where each point isn't a single frame, but an entire spacetime volume of pixels evolving across time. That's a large part of what sits underneath systems like Sora. The same straight-line, simulation-free training principle, scaled up to a domain where simulating a full stochastic trajectory during training would have been even more punishing than it was for still images. Concretely, video diffusion turned flow matching systems typically break a video into small spacetime patches, little cubes of pixels spanning both space and a handful of frames, and treat the whole collection as one giant point in an enormous space. The same straight-line conditional path, the same subtraction for a target velocity, the same regression loss, just applied to patches instead of pixels. Nothing about the mathematics needed to change, only the tokenization of the data did. That portability is exactly why one piece of 2022 theory ended up underneath both a single still image and an entire generated film. 4 years ago, diffusion models were the undisputed engine of generative AI, and stochastic differential equations were simply the cost of doing business. Flow matching didn't win by being a flashier idea. It won by noticing that the messy, random part of the problem was never actually necessary, and replacing it with a straight line and a subtraction. That's the real shift underneath every one of these systems right now. Not more compute thrown at the same equations, but a quieter, more elegant piece of mathematics doing the same job for a fraction of the cost. If you want the 15-second version of the moment those paths snap straight, it's already clipped below. And if this kind of deep dive is what you come here for, the rest of this channel is built for exactly that.